And control systems are indispensable in modern industrial processes, whether the industrial process is space technology, whether it is transportation system, whether it is robotics, or whether it is a power system. These are just a few examples I'm giving. In general, it has become part of our daily life. So with this background, let us go to the various, let us look into the various applications in power system first, and then we will go in detail about the load frequency problem. So the main outline is I will be defining what the problems in the load frequency control, what are the different problem statements that we'll be looking into. And this load frequency control will be tackled using the nonlinear sliding mode control methodology. And first, we'll be using only the nonlinear sliding mode control methodology. And in the next step, we'll be using a disturbance observer based nonlinear SMC. So before we start off with the main work, I would just introduce that the main objective of the power system operation and control is to maintain continuous supply of power, where the quality is also acceptable to all the consumers of the system. And the control theory will enable us to develop methods for effective control and operation of power systems. So whether it is a simple 2-area power system, or whether it is a multi-area power system, or whether it is a hybrid system where we have wind power penetration, any kind of a system that we look into will involve controls again there, because whether we want to maintain the frequency, whether we want to maintain the voltage, whether it is active power, reactive power, whatever it is, we need the use of control systems will definitely come into picture. The first problem in that could be encountered in the area of power systems is the load frequency control, wherein the objective is to maintain the balance between the load and the generation in all the areas. And at the same time, we want to minimize the transient deviations and the steady state error. And each area should also maintain the tie line power flow to whatever value is specified. The other problem in the power systems is the reactive power voltage control, where the voltage at all the terminals of the equipment in the system should remain within acceptable limits. And the system stability is enhanced to maximize the utilization of transmission system, and the losses we will try to minimize. The next problem in power systems is the economic operation of power systems, wherein it can be categorized into economic dispatch and optimal power flow. So this economic dispatch deals with determining the power output of each plant to meet the specified load, so that the overall fuel cost is minimized. And optimal power flow deals with the minimum loss delivery, wherein the power flow is optimized to minimize the losses in the system. So this economic operation of the power system is categorized this way. And the other problem encountered in the area of power systems is the unit commitment. And here, the objective is to get the operational and optimal power flow constraints by meeting the security and economy, and to formulate in exhaustive combination of units in real time. And then it is computer control of power systems, another area. And here the objectives are categorized into primary, secondary, and tertiary objectives. The primary objective is the security and stability of the system, and the secondary objective is the economic operation and control, and the tertiary objective is the optimization, operational planning, and maintenance and scheduling. And another very upcoming area is the cyber physical security of power systems that I haven't included in the slide, but that is also a very upcoming area of research in the area of control applications in power system. So with this background, we'll start with the load frequency control. We'll be focusing on the load frequency control problem. And when we talk about the load frequency control, again, when we talk about the power systems in general, we have two independent control issues. One is the load frequency control and the other is the reactive power and voltage control. Now, these two issues are supposed to be independent because their time constant, there is a difference in their time constants. When we talk about the different time scales of the power systems, power system control schemes, we have the protection scheme will be functioning in milliseconds, whereas the AVR, FACS, or the power system stability, all these will range from milliseconds to seconds. And when we talk about frequency and tie line controllers, these will range from seconds to minutes. That is why these two problems, that is the active power or the load frequency control and the reactive power control, they are considered to be two independent of each other. And this load frequency control is also known as automatic load frequency control, power frequency control, real power frequency control, automatic generation control. So in the literature, you can see that all these terminologies are used, but then it simply means we are talking about the load frequency control. And the load frequency control has two primary objectives. The first objective is to maintain the frequency at a constant, whether it is 50 hertz, 60 hertz, it should remain constant even if there are any variations in the load. And the second objective is every area must maintain the tie line power flow to the pre-specified value. So it is, we do not want any deviations in the frequency. We do not want any deviations in the tie line power. These are the two objectives that need to be met when we talk about the load frequency control. And the load frequency control has two control loops, the primary control loop and the secondary control loop. So the primary control loop provides the defensive action and it regulates the governor valve position automatically. It establishes a balance between the generation and the demand. And it is always in action, and it is the time frame is from milliseconds to seconds. And when we talk about the secondary control loop, it is the control by which the turbines respond to commands issued by external entities. And this secondary control loop restores the power interchanges with adjacent areas to their specified values, and to restore the system frequency to its set point value at the same time. And this takes varies from seconds to minutes. And its functions are executed both within the power plant and in the balancing areas. So when we talk about the load frequency controls, we will be having two loops. One is the primary control loop and the other is the secondary control loop. So the PI action in the LFC problem is inbuilt, but then this PI action alone will not be sufficient at times to maintain the frequency deviation to 0 and the tie line power deviation to 0. That is where we need to augment the system with some supplementary control. So now this is the block diagram for the LFC problem for a two area control system. The upper one is the area A and the lower one is the area B, and the two areas are interconnected via the tie line power. And the two areas are interconnected via the tie line power. And here you can see that both the areas, they have the integral control coming into picture. They have the integral control coming into picture here. This is the secondary control, and the primary control is the droop control, which is coming into picture in this part. So this has a droop control and an integral controller. And this is the governor. And this is your turbine generator. And this is the rotating mass. And these are the frequencies of area A and area B. And this is the tie line power. And this is the tie line power. So we want the tie line power deviations to be 0. We want the frequency deviations to be 0. So with this objective, and let us go ahead. So in the literature, there are several methods reported for the load frequency control. One of the methods is by simply tuning the PI controller gains. This is the classical control method. And the drawbacks of this classically tuned PI controllers is that they have a longer settling time and an unacceptable undershoot or overshoot. And they are giving a satisfactory performance only in the vicinity of the operating point. And if the load variations shift the operating point a little drastically, then this can cause oscillations and even instability, thereby deteriorating the performance of the system. So these PI controllers work satisfactorily only under very restricted conditions. So to overcome these problems, some robust and adaptive control methodologies have been reported. Even intelligent control and optimal control methods have been reported. And the operating point will shift because of uncertainties, because of some environmental conditions, and because of the changing structure. So to cope up with all this, we need some robust methods so that the performance of the system does not deteriorate. So one robust control method, which is very extensively reported in the literature and extensively used also, is the variable structure system control theory. And to implement this variable structure control theory, we need the information of all the states. That is, the states must be completely known to us. And the other very important characteristics is that this variable structure control theory is not sensitive towards uncertainties and non-linearities. So this is this is a very beautiful property, and only because of this property, this variable structure control theory has become very popular. The variable structure control theory can again be used in the centralized way or a decentralized way. So when we use it in the centralized way, this operation becomes a little complex because the size of the system will increase and all the state information will be required here. But if it is used in the decentralized way, then the resulting control algorithm becomes less complex because it requires only local information of these states. So this is again here, because we are not getting the satisfactory response here. So what we are doing is we are introducing some supplementary control, and this supplementary control is introduced here for area A and here for area B. And by introducing this supplementary control, we will try to get a much better performance. So this supplementary control is based on the variable structure control theory. And the variable structure control theory based sliding mode control scheme can be applied for both matched uncertainty as well as unmatched uncertainty. And because it's a very robust scheme, it improves the steady state response in the presence of uncertainties. But the improvement in the transient response is not as expected. It is good, but it improves, but not as expected. So this is the reason why we are talking about non-linear sliding mode. This is a linear sliding mode control scheme that we are talking about here. And the demerits are the oscillations in the presence of system non-linearities. So when we talk about load frequency control, the load this problem can be approximated as a linearized system because it has a slow convergence rate. But then the non-linearities that are present in the load frequency control, that is the generation rate constraint and the governor deadband, because of this these non-linearities, the system performance deteriorates. And the other demerit is the chattering effect. This chattering effect is coming into picture because of the discontinuous signal that we are applying in the sliding mode control. In the sliding mode control, one is the nominal controller, which is nothing but the equivalent controller, and the other is the switching control that we apply. And because of the switching control, we have the chattering effect. So there are different schemes reported in the literature to reduce the chattering effect. Some are using the higher order sliding mode, the super twisting algorithms, fuzzy sliding mode control, and nonlinear sliding mode control. So all these methods will reduce the negative effects of chattering. That is, it will reduce the chattering. And the LFC scheme, and when we talk about the load frequency control, the effect of time delay is also very common. We will not be talking about it, but this is also very common when we talk about the load frequency control. And this time delay has a very negative effect on the performance of the system. It not only degrades, but sometimes it even makes the system unstable. And when we talk about this time delay or the communication delays, they are because they can be categorized again into constant delay, time varying delay, or random delay. So when we talk about delay again, when we introduce delay in the system, this is a practical